Hello, my name is Vineeth, and I'll be presenting my final project, kidney cell type classification from single cell RNA sequencing data. The goal of this project was to classify kidney cell types using machine learning based on single cell RNA sequencing data. So, why this project? Because precise cell classification is critical in understanding kidney transplant biology, disease mechanisms, and even therapeutic responses. Machine learning offers a scalable way to do this reliably. I was inspired by prior work and work being done internally at the company that I work for, and this paper from which the data originated from that evaluated five machine learning algorithms on the same data. They achieved a median F1 score of 0.94, and I wanted to see how close I could get to that. Crucially, the study emphasized that dimensionality reduction and hyperparameter tuning were pivotal, and this told me that modeling decisions, more than just the choice of model, are key factors that I should be considering. So, the data description. The data came from a kidney transplant study and was stored in an RDS file, a CIRAT object. This format is common in bioinformatics, but difficult to use in Python. So, I used the RPY2 package to bridge R in Python. Each cell had expression levels for tens of thousands of genes. So I was working with a high dimensional, sparse data set. Challenging, but also realistic in biology. During exploratory data analysis, I noticed a few things. First, I built a distribution using the Surat clusters as my class distribution variable. And I found that cluster 0 dominated with over 2,300 cells in that cluster. This imbalance would absolutely bias the model. Second, I found there was a strong correlation between two features, the N count RNA and N feature RNA, which does make sense biologically. However, I found extensive missing metadata in key fields like sex and sampling location, which means I really wouldn't be able to use these features as much in training my model. Two additional findings stood out. Most genes had low variance, meaning they weren't informative. That confirmed the need for dimensionality reduction. And from the correlation heat map of top variable genes, I saw biologically meaningful co expression blocks, suggesting regulatory patterns that the model could learn from. So, the next step for me was to pre process this data. The pre processing pipeline was fairly involved. I extracted RNA counts and metadata from the Sirats object, normalized expression values, and applied PCA via truncated SVD. Dimensionality was reduced to 100 components, a trade off between preserving variance and keeping training tractable. For my first machine learning approach, I chose a random forest model, robust, interpretable, and less sensitive to overfitting on small datasets. I used five-fold stratified cross-validation, tuned key hyperparameters, randomized search CV, and used PCA components as features. So the results of this was that the model delivered a solid macro F1 score, but the confusion matrix revealed trouble distinguishing between closely related cell types. Using SHAP, I saw that principal components 1 and 2 drove most of the predictions. That's not ideal. Over reliance on just a couple of features hint at potential overfitting. Also, some cell types were consistently misclassified, suggesting the model wasn't capturing more complex patterns. So, I planned three specific improvements for my second approach. I wanted to try a more powerful model, like XGBoost, to better handle complex interactions. I also wanted to tune hyperparameters more thoroughly with Bayes search cross validation, and I wanted to reduce overfitting from dominant principal components by removing low value features or using regularization. For my second approach, I switched to XGBoost with Bayesian hyperparameter optimization. I reduced the cross validation to threefold for speed, and I reused the same PCA inputs for a fair comparison. This model trained faster and showed stronger learning capacity right away. And the results kind of speak for themselves. XGBoost outperformed Random Forest across most metrics. Accuracy went from 0.86 to 0.87. Macro F1 improved from zero point 0.7 to 0.74. Recall increased as well, meaning the model was less likely to miss a positive class. And the confusion matrix showed less off diagonal mass, so fewer misclassifications. The SHAP plots also told an interesting story. Random Forest had a flat distribution. Feature importance was spread out, which helps with robustness but limits focus. XGBoost, on the other hand, was dominated by PC1 and showed sharp class specific patterns. That indicates deeper, more decisive learning. In summary, both models were successful, but XGBoost provided better performance and better class separability. Bayesian tuning made a really big difference in efficiency, and the model is better positioned for practical use. So workflow could also be adapted for foundational model training and to other real world applications in diagnostics or biomarker discovery, especially where cell type classification is key. And that's that. Thank you for listening.